So we're dealing with kinematics here. Kinematics and dynamics, which are the first two units, have a lot of overlap. Okay? Kinematics deals with just the motion of the objects. So kind of the stuff we looked at a bit in Science 10. So velocity, displacement, speed, distance, time, acceleration, okay, things like that. It just looks at the motion itself. It doesn't look at why that motion is occurring. That's what dynamics does. Okay? Dynamics looks at the forces involved in making an object move, the energy involved in getting those forces going, okay, work and all of that kind of stuff. That's what dynamics focuses on. So we'll be looking at similar situations in those two units, but from different perspectives. Okay? So for lesson 1 here on kinematics, this is going to be, as I said before, mostly review. Okay? We're going to understand that the motion of objects and systems can be described in terms of displacement, time, and velocity. And you could probably add to that distance and speed, okay, as well. Okay? We're going to look at, compare, contrast scalar versus vector quantities, okay, and define velocity as a change in position during a time interval. Okay? So reviewing basically V equals D over T. Right, from last year. Okay, what's the difference between a scalar and a vector quantity? Anybody remember from Science 10? What does a vector quantity have that a scalar quantity doesn't?
Direction and magnitude.
Right, a vector quantity has magnitude and direction, just like, you know, the little villain in Despicable Me. Okay, and scalar quantities only have a magnitude. Okay? So as an example, all right, mass is a scalar quantity. Okay? Mass measures how much of something there is. Right? So my mass is about 82 kilograms. Okay? That's how much of me there is. I wish there was less, but that's what it is. Okay? My weight, on the other hand, is a vector quantity. Weight is the force of gravity pulling my mass downwards, okay? And it would be somewhere in the neighborhood of probably 795 newtons down. It's a vector quantity, okay? It has magnitude, 795 newtons, but it also has direction, down, okay? Everyone kind of follow me there? Okay? A better example might be displacement and distance. Okay? Distance measures how far you go. Okay? Whereas displacement measures how far and in what direction from where you started do you end up. All right? Now, in Science 10, if you were in my Science 10 class, I might have asked you this question. How far is it to Edmonton? Okay? And our gut reaction, for most of us, is to tell me how long it takes to get to Edmonton. Okay? Most people, you ask them, how far is it to Edmonton? And they said 3 hours. Is that what I asked? Does how far mean the same thing as how long? It doesn't. Okay? But it's a cultural thing, okay, that most Western countries have a problem with. Okay? When people ask us how far it is, they tell us how long it takes to get there. Okay? It's something we have to watch out for in physics. Okay? If the question says, how far is it? It actually wants something in meters or kilometers or something like that. It doesn't want something in seconds or hours. Okay? That can be very, very misleading for people. Okay? In fact, it can sometimes even result in people getting into dangerous situations. Okay? It happened to me and a friend years ago when we were backpacking, okay, through Kootenai National Park. Okay? We had hiked about 34 kilometers, and we thought we should be at the campground already, and we weren't. And so we were kind of concerned maybe we'd taken a wrong turn and gotten lost. So we sat down and drank the last of our water, and I'm kind of like, well, what do we do? And we see this guy come like bebopping up the trail towards us. He's literally running uphill, wearing at least 60 to 70 pound pack. Okay, and he is running what appears to be effortlessly towards us uphill. And we're like, hey, dude, did you come from Tumbling Creek Campground? And the guy looks at us and he's like, oh yeah, Mike, it's just down the trail about 20 minutes. And we're like, oh sweet, it's like 20 minutes. An hour later, we're stumbling into this campground, cursing this guy, okay? We didn't think about that we had asked him how far it was, and he had told us how long it took him, as probably some sort of special forces guy out for a training run with his heavy pack. Okay? He was literally running uphill for two out-of-shape teachers on their summer vacation. Okay? Of course we don't go as fast as him. Okay? Of course it took him 20 minutes and us an hour, which we eventually figured out when we got some food in us and some more water, and we started being logical, and then we felt really embarrassed because we were both physics teachers. And I looked at my buddy and I'm like, Sean, do you know what we just did? And he's like, shut up, we tell no one. Okay? Because he knew we accepted how long it took instead of how far it was. Okay? The guy had told us it was 3 kilometers. We didn't know it would have taken us an hour. Okay? But he didn't. And we allowed that. So, how long, how far, 2 different things. Okay? All right. So, example here. In each case, I mean, there's nothing wrong with a scalar quantity versus a vector quantity. In a lot of cases, one is appropriate and the other is not. Okay? But vector is not always better than scalar. Scalar is not always better than vector, but there are situations where one is better than the other. Okay? So if I'm looking at, going from Okotoks to Calgary, okay, would I tell someone a scalar quantity or a vector quantity? If they said, how far is it from Okotoks to Calgary, what would I tell them? Would I probably tell them like 38 kilometers? Okay, is that okay? It's a scalar quantity, but is it okay? What am I assuming they're going to do? Yeah, get on the road and follow the road and read the signs. Okay? In that situation, I don't need to tell them what direction to go. I mean, unless they're like from, I don't know, Venezuela. Maybe they don't know the geography of Canada. Okay? But I mean, generally, people would know that Calgary is north of here. Okay? I don't necessarily have to tell them that. I can tell them it's 36, 37 kilometers from here, and they'll get on the road and they'll follow the signs and they'll get there. Okay? In that case, scalar quantity is perfectly fine. All the road signs use scalar quantities. When you're driving along the highway, okay, it says, Claire's home, 42 kilometers, okay? Or it says, Bragg Creek, 16 kilometers. It doesn't say west or south. It just assumes you're going to keep going along the road, okay? A scalar quantity is totally appropriate in a situation like that. Now, if I'm flying an airplane from Okotoks to Calgary, do I need a direction then? I'm not going to follow the road. I'm in a plane. I don't have to follow the road. Okay? That's the whole advantage of being in a plane. I can go basically wherever I want. Okay? Then I'd probably want a vector description. I'd want to know what heading to point my plane so that I would get there. Okay? Everyone kind of following the difference? One is never better than the other. Okay? One just gives information differently. Okay? All right, so a more descriptive description, and vector quantities are more descriptive, they give an additional piece of information, okay, would be to give them the vector description. Okay? That doesn't make them more accurate. Okay? People often think that just because a vector quantity gives something else, gives like it's this direction as well, that makes the vector quantity more accurate. Okay? It doesn't. Right? I could easily do this. Okay, say that Calgary is 38.025 kilometers, or I could say that Calgary is 38 kilometers at, let's say probably 13 degrees west of, okay? The bottom one's a vector quantity, the top one is scalar. Which one's more accurate? Somebody's got to have an idea. Do I have to get the random student selector? They just put this new feature on PowerSchool. It's called the random student selector. I just push a button to pick somebody's name. Do I have to do that? Can somebody tell me which one's more accurate?
The scalar one?
The scalar one. Okay? It's measured to the nearest thousandth of a kilometer. Okay? That basically means that it's measured to the nearest meter. This one's measured to the nearest kilometer. So when I get this measurement, I know that Calgary is that far, plus or minus 1 meter. That's that far. Okay? This one here means that Calgary is somewhere between 37 and 39 kilometers. Okay? Is that a lot less accurate? Okay? That's like me, giving you guys different meter sticks and making you measure the distance around the track. Okay? If I give you a meter stick that's got millimeter markings on it, when you get done measuring the track, you'll know to plus or minus 1 millimeter how far it is around the track. But if I just give you a stick that's a meter long and it doesn't have any marks on it, you're only going to be accurate to plus or minus 1 meter. Okay? So it's how you measure something, okay, not what you measure, that determines your accuracy. Okay. All right, so for vectors for us in physics 20, okay, we'll start out with just the positives and negatives, or rights and lefts and ups and downs like you did in science 10. Okay? But we're eventually going to get to this, compass directions, okay, to degrees. So that's where the trigonometry will come in. All right, so let's say we got this situation here. Okay? Let's say that I want to walk from my house to Walmart. Okay? Can I walk in a straight line from my house to Walmart? You don't need to know where I live to answer that question. Okay? There's no chance. Okay? Even if you live right beside Walmart, there's a fence between that line of houses and Walmart. You can't walk in a straight line. You have to walk around the fence. Okay? So it's impossible to walk in a straight line from your house to Walmart, no matter where you live. So you got to follow like the paths and the roads and the sidewalks and whatever. Okay? So that would be the black line. If I walked from my house to Walmart, I would follow that black line. Now that black line changes direction a whole bunch of times. Would you agree? Okay. So when I measure how long that black line is, and I say that that black line is 4 kilometers, I'm giving you the distance. I'm telling you how far I had to walk to get from my house to Walmart. It's a scalar quantity. It's just how far I went. Okay? It's what the odometer in your car reads when you drive from one place to another. It tells you how far you drove. Okay? Now, the purple line, okay, is the displacement. Displacement is your change in position with direction. So it's the vector version. So unless you were able to walk in a straight line, displacement is always going to be shorter. Okay? Because obviously the shortest route between 2 points is a straight line, and displacement's always that straight line. Okay? So if I had a helicopter, I'd go this way. Well, I also wouldn't shop at Walmart if I could afford a helicopter, but okay, that's beside the point. So I could fly straight there. And that would only be 2.8 kilometers. Okay? And it would probably be looking at that, probably 47 degrees west of north. I'm going to put a vector on that. Okay? Everybody all right with that? Okay? So are they talking about the same trip? Okay? Displacement and distance talk about the same trip. They're just looking at it from different points of view. Okay? One is looking at how far did I have to go to do this, and the other one is looking at how much did you change your position and in what direction from where you started. Okay? So same story, different points of view. Right? If you're a Star Wars geek like me, okay, Obi-Wan Kenobi told Luke Skywalker that Vader betrayed and murdered his father, and then he found out later he actually was his father, but it was just two different points of view. It was the same story. Okay? That's what distance and displacement are doing. They're telling you the same story from different points of view. Okay? All right. Let's say that that trip takes me a half an hour. Okay? How fast did I go? What is how fast asking you for? Speed or velocity? Okay, police officer walks up to your car, you're pulling you over. You know how fast you were going? What does he want to know? Speed or your velocity? Your speed. He's not going to give you a velocity ticket. Okay? He's going to give you a speeding ticket. All right? So, how fast is your speed? And we calculate speed by dividing distance by time. Speed is scalar, so it goes with the scalar quantity distance. Okay? So, I walked 4 kilometers in 0.5 hours. Okay? I walked 4 kilometers in half an hour. How fast was I walking?
8 kilometers an hour.
8 kilometers an hour. Okay, 4 divided by 0.5 is 8. Okay, and my units would be kilometers over hours, or kilometers per hour. Okay, that would be my speed. Okay, what's my velocity?
Displacement divided by time.
Displacement divided by time. Okay, so velocity is a vector quantity, so it gets the little arrow over top. Okay, displacement's a vector quantity, it gets the little arrow over the top. Time's the same, right? We're talking about the same trip. Takes the same amount of time. All right, so then for this one, I've got 2.8 kilometers at 47 degrees west of north, divided by 0.5 hours. Okay, when I do that, just multiply that by 2. Okay, 5.6 kilometers per hour at 47 degrees west of north. Is it okay that the vector doesn't change? It's more than okay. It's vitally important. Okay? Have you ever gone south by driving north? Okay? Since it's impossible to drive across the ocean. No, you've never circumnavigated the Earth. Okay? Because that'd be the only way that that could happen. Okay? Your vector for your velocity and your vector for your displacement are always going to be the same because one is a measure of the other. Okay? Velocity is a measure of how quickly you change your position. Displacement is how much you change your position. They have to have the same vector because they're going the same places, okay, at the same time. Is everybody okay with that idea? So there's no extra calculating. Good news. Okay? Your vector for your displacement and your vector for your velocity will always be the same. Okay? Mathematically speaking, there's nothing to cancel it off or change it when I divided it, was there? Time is scalar, so it couldn't change that number. Okay, so I'm getting old and forgetful. So I get to Walmart and I discover I have left all my methods of payment at home. Okay, so I don't even bother walking into the place. I just turn around and walk back home. That's never happened. Okay, but let's just say it did. So I walk home along exactly the same path. What's my total distance traveled? 8 kilometers. Okay, if I walk the same path back, I walk a total distance of 8 kilometers. Okay, what's my total displacement?
0.
0. Okay, remember what displacement measures. It's your change in position. If my starting position is home and my final position is home, have I changed my position? I've not. Okay? Therefore, my displacement would be 0 because the start and end point of my trip is the same place. Okay? This is exactly why the odometer in your car measures distance and not displacement. Okay? If it measured displacement every time you came home, it would basically reset itself. Well, it would tell you how far it is from the dealership you bought the car at to your house. Every time you go for an oil change, it'll read 0. Okay? But otherwise, it's basically never going to change because you're always going to come back to your house. Okay? That would make your odometer, well, very favorable for you when you go to sell your car because it'll have next to no miles on it. Okay? That's why exactly it measures distance. People need to know how far have you driven that car. Okay? Everybody all right with that idea? Okay? So here's another example of a vector quantity is inappropriate in this situation, appropriate. A scalar quantity is more appropriate. Okay, so if I've gone back home, took me a half an hour to go back home, did I still walk at a speed of 8 kilometers per hour in total? Yeah. I still walked 8 kilometers in 1 hour. Okay, it's exactly 8 kilometers per hour. What's my velocity now that I'm home? Think about this formula. What did we say this number was when we got home? If I end up back at home, my displacement was
0.
0. So what's my velocity?
0.
0. 0 divided by anything is 0. Okay, remember, velocity is the rate at which you change your position. If you don't change your position, there's no rate of change of position because you didn't change it. Okay? That's where it's helpful to know the definitions, okay, of all of those things, of speed, of velocity, of distance and displacement, so that you know when one it might be 0 and one might be something else. Okay? Is that ringing a bell from Science 10? Okay. So, distance, speed, and time are scalar quantities. Okay? Velocity, displacement are vector quantities, and we treat them a little bit differently. Okay? Okay, let's say I'm in this situation. I'm here at Seldom Inn Campground, and I'm going to walk to here. This is Snake Indian Falls Campground. There's a sign just outside of Seldom Inn Campground that says Snake Indian Falls Campground, 38 kilometers. What is it telling me?
Distance?
It's telling me distance. Okay? It's telling me how far I will have to walk to get there. What is it assuming I'm going to do?
Follow the trail.
Follow the trail. Little dotted lines on that map are trails. It's assuming I'm not going to be crazy, okay? And I'm going to follow the trail. Because if I follow the trail, it'll be the easiest path from one to the other, not the shortest, the easiest. Okay? There'll be bridges over all the rivers and everything. Okay? That's the best way to go. Okay? That sign does not read Snake Indian Falls Campground, 18.9 kilometers at 53 degrees west of north. Okay? Now, if I had a helicopter, that would be the way I would want to go. Okay? But I can't walk this way. This is a glacier. Okay? This gray stuff is a glacier. Okay? All of these rivers are going to have deep, treacherous canyons. Okay? That is not the smartest. It's the shortest way, but it's not the smartest way to go. Okay? It's like we said before. Road signs tell you distance, because in that situation, scalar is more appropriate than vector. Okay? But if you're going to be a pilot, or you're going to be like a navigator on a cruise ship or a cargo ship or something like that, okay, you definitely need to be able to do vectors, because that's what you're going to have all the time. You're going to need to know your vectors, your headings, okay, all of that kind of stuff. You know, if you're going to drive a train, well, it's kind of less important. You kind of have to go where the rails tell you to go. Okay? Then you'd be dealing with scalar stuff more often. Okay? All right. Okay, so speed and velocity talk about similar things. They both tell you how fast you're going, basically. All right? But one tells you how fast and in what direction, and the other tells you how fast. Okay, it's like we said before. A police officer walks up to your car. He doesn't ask you what your velocity is. Okay? Nor should you tell him. Okay? Because if he says, how fast were you going, and you answer 128 kilometers per hour at 32 degrees east of south, he's going to have a follow-up question. How much have you had to drink or smoke today? Okay, because that's a really weird way to answer that question. He is not looking for a vector quantity when he asks you that question. Okay? He is looking for a scalar quantity, okay, on that question. He wants to know you were going 128 kilometers and you were going way too fast. Okay? All right. Questions on the differences there? Okay, hopefully that's ringing a bell for everybody. Okay, so just quick definitions here. Okay, a scalar quantity is any measured quantity that has only a value or only a magnitude. Okay, so like 7 days or 200 kilograms or 60 kilometers or 5.3 meters. Okay, all of those things are scalar quantities. Even 100 kilometers per hour would be a scalar quantity. Okay, they're just a magnitude, a measured value, and that's it, and units. Okay. Distance, scalar quantity that measures how far an object has traveled. Just how far, doesn't care what direction. Could have gone back and forth 100 times. Okay, it's still only caring how far did it go when it went back and forth 100 times. Okay, speed is a scalar quantity that measures how far an object travels in a set time interval. Okay, or how fast it's going. Okay, kilometers per hour, or more often for physics, meters per second. Now, vector quantities are any measured quantity that has both value or magnitude and direction. 40 kilometers forward, okay? 798 newtons down, okay? 60 kilometers per hour north, okay? Things like that. You could have 9.81 meters per second squared down. That's an acceleration. It's a vector quantity, okay? Things like that. So anything that has magnitude and direction. Okay. Displacement, okay, vector quantity that measures how far and in what direction an object has traveled from its starting position. We sometimes even write this like this, that displacement is final position minus initial position. That we use a lot when we're dealing with a position versus time graph that might ask us, what's the displacement of this object? Okay, and then velocity is a vector quantity, okay, that measures the displacement of an object during a set time interval. Okay, so displacement over time, the rate at which you change your position. More often than not, that's going to be in meters per second, okay, as well. Okay, and then we've got our formulas. Okay, speed is distance over time, that's v equals d over t. Velocity is displacement over time, so that's v with the arrow over top equals d with the arrow over top over time. Or we can also write it in its extended form. It could also look like this. Final position minus initial position over time. Okay, it could also be written like that. Okay, ringing a bell from last year, all of that? Because I have not taught you anything I wouldn't have taught besides this thus far. Okay, now, just a note on algebra. I'm going to assume that you are here because you no longer require triangles to manipulate equations. Okay, I hope and pray that that's the truth. Okay, because while yes, you could draw a triangle that would solve a v equals d over t problem, that is not going to last. Okay. More often than not, in this class, we're going to have formulas that are far more complex than that. Okay, give you an example. Don't know that you'll find a triangle that will manipulate that one for you. Okay, it's got a radical in it. That's going to be somewhat difficult to use a triangle for. Okay. Or this one. There's a lot more than 3 things in that formula. Okay, so if you've been relying on the triangle, you have to break that habit right now, right? Because once we get to acceleration, you're done with the triangle. Okay, we deal with a lot of acceleration formulas like this one. Maybe a rhombus will work for that. I don't know, but I'm pretty sure you're out of luck on that. Okay, so if that's been something you've been using, okay, you're not going to be able to use it here. Okay, let's look at a simple vector, scalar, calculate displacement type of question here. Okay, so in this question, this person is standing 1.5 meters to the right of the Inukshuk. So that makes this their initial position. Okay? A little while later, they move so that they are now 3.5 meters to the left of the Inukshuk. Okay? That would be their final position. Could I calculate their displacement? Okay? Will this formula that we looked at just a minute ago work? Okay, do I have all of that? What do I have to be mindful of? I can certainly use that formula, but my starting position is 1.5 meters to the right. My final position is 3.5 meters to the left. Okay? Is there a change in direction here? I mean, they don't actually change direction, they always walk left. Okay? But my initial position has a different direction than my final. What do I have to make one of them to reflect that? Negative. I gotta make one of these negative. Okay? I mean, if we just look at this logically, what's their displacement without doing really any math on paper? They started out 1.5 meters to the right of the Inukshuk and they ended up 3.5 meters to the left. How far did they go?
5 meters left.
5 meters left. Okay? I don't really have to do a lot of like on paper math to figure that out. Okay? But in order to get 5 meters left, okay, I've got to go negative 3.5, make left negative, minus 1.5. When you go negative 3.5 minus 1.5, you get more negative. Okay? You get negative 5.0 meters. Okay? And since negative is left, their displacement is 5 meters to the left. What's their distance traveled? How far did they walk?
5 meters.
5 meters. Just don't put the left on it. It was a straight line, right? In this case, displacement and distance are the same magnitude, right? One has a direction, the other doesn't. Okay? But they had to walk 5 meters in order to do that. Okay? Everybody all right with how that worked? Okay, so that's how that formula can work. But we have to be mindful. We're dealing with vector quantities in here, which means if one is left and the other is right, one's negative, one's positive. Okay? Okay, I would like you guys to try those 3 problems there. Okay, give you a few minutes on those and then we'll go through them together. Okay, so number 1, all of them go north. Does that make it easier? Okay, because they don't change direction, right? I can just make everything positive because everything is north. Okay, so if I want to know the sprinter's displacement, I go 40 plus 20 is 60 plus 100 is 160 meters north. Okay, and that's all I have to do for that one. Okay, 160 meters north. They're all north, they're all the same. What does that mean their distance was? How far did they go?
160 meters.
160 meters. Okay? They didn't change direction. Okay? So in this case, they got another straight line traveling path where the displacement and the distance would have the same magnitude. Okay? How many people have done the second one? Okay, let's have a look at that one. All right, so to perform a give and go, basketball player fakes out the defense by moving 0.75 meters to the right and then 3.5 meters to the left. What is the player's displacement from their starting position? Okay, so here's their starting position. Okay, they move 0.75 meters to the right. Okay, and then from there, they go 3.5 meters to the left. Okay, so their displacement is obviously left of where they started, but how much left?
2.75 meters.
2.75 0.75 meters. Okay, we went 0.75 meters to the right, then we went 3.5 meters left. We just subtract that travel right from there. Okay, this has to be 2.75 meters to the left. Okay, everybody all right with that one? Okay, all right. Give you a couple minutes on number 3 since you couldn't see it before. You won't take you long. Okay, so let's look at this one. So just for context, probably none of you have ever built a brick wall, okay? But when you're putting bricks like these cinder blocks on the back wall together, okay, you don't just lay them on top of each other and walk away. Okay? You put mortar or cement in between them and it fills the holes, and then it fills the holes in both bricks and it makes them one big brick, because it ties them together with concrete. So what this person is doing is they're just pushing that concrete back and forth with the trowel. Okay, so they go 1.7 meters out, 1.7 meters back, 1.7 meters out, 1.7 meters back. What's their total displacement? 0. They ended up back where they started. Okay, they went out and back twice. Okay, that means they ended up back where they started. So their total displacement is still 0. Their initial position and final position are the same place. Okay, but their total distance would be 1.7 times 4. Okay, because they did that 4 times. Okay, so what we end up with there, okay, is 6.80 meters for the distance, 1.7 times 4, and 0 meters, okay, for the displacement. Now, displacement is supposed to be a vector quantity. Why didn't I put a direction on that?
Because you went back to where you started, so you didn't change direction.
Right, with no displacement, there's also no direction. Okay, now for each one of these questions, okay, even for this one here with the brick lane, okay, we went out, back, we had a starting position. Okay, this one here had a starting position. Even the first one, okay, where they went 40, 20, and 100, had a starting position. Okay, we have to have a reference point from which to measure all this stuff when we're doing a problem like this. Okay, choosing that reference point is important. Okay, so I want to illustrate the importance of a reference point with question number 4. I want you to draw that seating plan. Okay, draw that seating plan for me, and then tell me who was the reference point. Okay, so they're just in a line. Okay, it's like basically along the table.